In the previous video, we looked at a few different measures of spread. They were the range, the interquartile range, and the interpercentile range. In this video, we're going to look at two more. They're known as the variance and standard deviation. Let's take this green set of numbers here, and this red set of numbers here. And we're going to try and answer the question, which one is more spread out? You might want to pause the video and make your decision. One way of looking at this is by plotting them on a number line. So if we have the green set of numbers, which looks like this, and the red set of numbers, which looks like this. Let's first of all consider the range, the difference between the greatest value and least value. So the difference between these values here is the range of the red numbers, and the difference between these two is the range of the green numbers. So you can see visually very easily, the green set of numbers has a higher range, so using this measure, the green set is more spread out. One thing to note about the range is it doesn't matter what the values are in between the greatest and least value. We can move these values around anywhere as long as they stay in between, and we still end up with the same conclusion, that the green set is more spread out. If instead we use the interquartile range, we find the difference between the upper and lower quartiles. So for the red set of numbers, that's the difference between these two, and for the green set of numbers, the difference between these two. This time you'd end up with the opposite conclusion. You would decide that the red set of numbers is more spread out. Just like with the range, we can move some of these numbers around and the conclusion won't change. If we move the numbers in between the upper and lower quartiles around, we still end up with the same interquartile range. So if the numbers were here or here, we'd end up with the same result. We can also move the numbers outside of the upper and lower quartile around as well. So these numbers here. And once again, we'd end up with the same outcome. This is because the interquartile range also doesn't take into account every single piece of data. And that's the main difference between the interquartile range, the range, and the standard deviation and variance. The standard deviation and variance use every single piece of data in their calculations. Let's have a look at how we calculate the variance for the green set of numbers. Before we begin, we're going to label this data with a variable. Let's just call it x. Then we're going to work out the mean of this set of data, so x bar, which is the sum of x over n. So to find the mean, we add up all of the x values, and then divide it by how many there are, which in this one is 6. If you do this calculation, you'll find the mean of these set of numbers is 9, so x bar equals 9. We can add x bar onto our diagram. The next thing we're going to do is work out how far each of the values are away from the mean. The number 10 is 1 away from the mean, 7 and 11 are both 2 away from the mean, and the 1 and the 16 are 8 and 7 away from the mean respectively. And since the value of 9 is equal to the mean, we could say it's 0 away from the mean. If these differences between our values and the mean are quite low, the data won't be very spread out. If on the other hand they're quite high, then the data will be spread out. One way of calculating these differences is to subtract the mean from each of the data values. So each of the values x subtract the mean x bar, so x minus x bar. Let's do this for each of the data values. So we'll start with when x is 1. We need to do 1 subtract the mean, and the mean was 9 remember, so 1 subtract 9, which gives you negative 8. Notice on our diagram at the moment, this just says 8 because it's 8 away from the mean. If we add a negative though, this will indicate that this is 8 below the mean. If we do the same idea for the next data value of 7, we subtract the mean of 9, and 7 subtract 9 is negative 2. So we can add a negative onto this one as well to show that it's 2 below the mean. For the next one, we do 9 subtract the mean of 9, and 9 subtract 9 is 0. Then we have 10 subtract 9, which is 1, 11 subtract 9, which is 2, and 16 subtract 9, which is 7. These last three values were positive, that's because they are above the mean. Then in terms of how spread out this data is, it might make sense to calculate the average of these values, because it will give an idea of the average difference between the values and the mean. So if we add up all of the values we just calculated, and divide it by how many there are, which is 6, we end up with 0. This might be surprising at first, but if you give it some thought, this will actually always be 0. All of the differences above the mean will always be cancelled out by the differences below the mean. Therefore, it's not a very good way of comparing how spread out the data is. We need a different approach. The approach we use for the variance is to square all of these values instead. So we're going to work out x minus x bar all squared. If we do negative 8 squared, we get positive 64. Negative 2 squared is positive 4. 0 squared is 0, 1 squared is 1, 2 squared is 4, and 7 squared is 49. The effect of squaring is we remove all of the negative values, so if we add all of these values up this time, we won't get 0. So what we're actually going to do is find the mean of these numbers. So if we add all of these numbers together and divide them by how many there are, which is 6, we end up with this number here, 20.3 recurring. And this number is known as the variance. We give the variance the symbol sigma squared, where we use a lowercase sigma. We can write out a formula for calculating the variance. The first thing we did was subtracted the mean from all of the values and then squared this, so x minus x bar all squared. We then added up all of these values, so the sum of x minus x bar all squared, and then divided this by how many there are, which would be n. So this is the formula for the variance. The other measure I mentioned was the standard deviation. The symbol for the standard deviation is just a sigma, without the squared on it. That's because the standard deviation is just the square root of the variance. So for its formula, we just take the variance formula and square root it. So for the green set of data, we worked out the variance at 20.3 recurring. So the standard deviation, which is just sigma, will be the square root of the variance, so the square root of 20.3 recurring, which is 4.509 and so on. When you work out the standard deviation, it will share the same units as the original data values. So for example, if the original values were in meters, the standard deviation would be in meters. The variance, however, will be the square of this, so meters squared. If the original data was in, say, kilograms, the variance would be in kilograms squared. That might seem like a funny unit to use at first, but it's just a regular unit, you just put a squared on it. Now that we've found the variance and standard deviation for the green set of data, let's repeat this calculation for the red set of data. You might want to give this a go on your own first. So let's label this data with a variable, like x, and we'll need to work out x minus x bar. To do this, we'll need to work out the mean, x bar. We work out x bar by doing the sum of x over n. So we need to add up all of these values, and then divide it by how many there are, which is 6. And this one also has a mean of 9. So we need to subtract 9 from each of the data values. So 3 subtract 9, which is negative 6, 4 subtract 9, 8 subtract 9, 11 subtract 9, 13 subtract 9, and 15 subtract 9. Now that we have each of these values, we need to square them. So x minus x bar all squared. Negative 6 squared, negative 5 squared, negative 1 squared, 2 squared, 4 squared, and 6 squared. Then to work out the standard deviation, sigma squared, we add up all of the x minus x bar all squared values, and then divide this by how many there are, which is n, which is 6. If you type this into your calculator, you'll get 19.6 recurring. Then to work out the standard deviation, sigma, we just square root the variance, so the square root of 19.6 recurring, which will give you 4.4347 and so on. Now that we have the variance and standard deviation for the red set of data, let's bring back the green set of data and its variance and standard deviation and make a comparison. If we look at the variance for each set of data, we can see the variance for the green set was higher than the variance for the red set. The standard deviation for the green set is also higher than the standard deviation for the red set. If you have a higher variance and standard deviation, then the data is more spread out or more varied. So we could say, the green set of data has a higher variance or standard deviation. This means the data is more varied or spread out. So far, when working out the variance and standard deviation, we've used this formula here for the variance and this one here for the standard deviation. There's actually an alternative formula that you could use, and it looks like this for the variance and this for the standard deviation. In some situations, these new formulas are actually easier to use. A helpful way of remembering this formula is to say the mean of the squares minus the square of the mean. That's because this part here is the mean of the squares, because we add up all of the squares and then divide them by how many there are, and this is quite literally the square of the mean, the square of x bar. Let's take a new set of data and use these formulas to work out the variance and standard deviation. So this set of data here, which we'll call x. Looking at this formula, there's 3 things we're going to need to work out: the sum of x squared, n, and x bar. Let's start with the sum of x squared. To do this, we're going to need to square all of the x values and work out x squared. So if we square 2, we get 4, square 5, we get 25, and then if we carry on and square all of these values, we get these numbers here. Then the sum of x squared will just be the sum of all of these values. So if we add them all up, we end up with a total 996. Then moving on to n, that's just how many data values you have, and you can count 7. Then we need x bar, which is the sum of x over n. So this time we need to add up all of the x values, so not the x squared ones, and divide that by how many there are. So if we add up all of the x values, and divide this by 7, we find that x bar is equal to 10. We can now just take the formula for the variance and substitute in each of these values. The sum of x squared is 996, n is 7, and x bar is 10. We then just type this into the calculator, and you'll get this value here. To find the standard deviation, we square root the variance, so sigma equals the square root of this number, which will give you this number here. This formula is usually preferred if you have a list of numbers like this one here. It's usually quicker to do because we don't have to subtract the mean from each of the values before squaring them. Let's have a look at a worded question that you could get in an exam. In this question, it says, the data shows the number of minutes it took 10 students to travel to school. And we need to work out the variance and standard deviation. So here's the data. Now the good news is, just like some of the measures of location in the previous video, we can use the calculator to work this out for us. Let's have a look at how this works. The first thing we need to do is go into statistics mode, and then we press one variable, and we've just got a list here, so we can just type all of these x values in. So 6, 9, 10, and I'll speed this up now. And once you've entered all 10 of those values, you just press the execute button once, and a second time, and you'll be presented with these statistics here. Let's take a closer look at what's on this screen. So where it says sigma squared x here, that's the variance, 43.09. And where it says sigma x here, that's the standard deviation. So the standard deviation, if we say round it to 2 decimal places, would be 6.56. In this question, it said the data was about the number of minutes, so we can add units to these values. Remember, the standard deviation will share the units of the original data, so the standard deviation will be in minutes, but the variance will be in minutes squared. I'll just show you quickly how we do this on the older style calculator, just in case you're using one of those too. So to do this, we press menu setup, and then we go 6 for statistics mode, and one variable. Then we type in the data just like we did before, so enter all 10 of the data values, and slightly differently we press option over here, and number 3, and we end up with the same information here. Now you might be thinking, if the calculator is going to calculate these for you, what's the point in learning how to calculate them manually? Sometimes you may get a question that challenges your understanding of what the variance and standard deviation actually are, and it certainly helps to have an appreciation for how they're calculated. Next, we're going to look at how you calculate the variance and standard deviation for data that's in a table. To do this, we'll need to make some changes to the formulas. In the first formula, when we're working out x minus x bar all squared, for any of the given x values, we'll need to do this a number of times equal to the frequency associated with that x value. So for instance, if the x value is 0 games consoles, we'll need to do x minus x bar all squared 6 times. A faster way of adding all of these up is simply multiplying x minus x bar all squared by the frequency. So we'll need to change the formula to the sum of f lots of x minus x bar all squared. When we have a frequency table like this, n is the total frequency, so we can replace n in the formula with the sum of f. We also need to make some changes to the alternative formula. In a similar way to how we added f to the numerator of the previous formula, the sum of x squared needs to be the sum of f lots of x squared. Once again, we can replace n with sum of f, and we already know how to work out the mean x bar from a frequency table. It's the sum of fx over the sum of f, so we can replace that in the formula too. So we have these two formulas here. Let's use the top formula to work out the standard deviation from this table. The first thing we need to do is work out x bar, the mean. We can do this by adding an fx column, multiplying the games consoles by the frequency, so 0 times 6 is 0, 1 times 13, 13, 2 times 10 is 20, and 3 times 1 is 3. Then if we add up the fx column, we get the sum of fx, which is 36, and if we add up the frequency column, we get the sum of f, which in this one is 30. Then to find the mean x bar, we do the sum of fx, 36, divide by the sum of f, 30. And for this one, you'll get 1.2. So the mean is 1.2. Next, what we're going to do is look at this numerator of the formula. We're going to work out x minus x bar. To do this, we subtract the mean, which we found at 1.2, from each of the x values, where the x values are the number of games consoles. So we need to start with 0 subtract 1.2, which is negative 1.2, 1 subtract 1.2, which is negative 0.2, 2 subtract 1.2, which is 0.8, and 3 subtract 1.2, which is 1.8. Then in the formula, we need to do x minus x bar all squared. so we just square each of these values to get x minus x bar all squared. The square of negative 1.2 is 1.44, the square of negative 0.2 is 0.04, 0.8 squared is 0.64, and 1.8 squared is 3.24. Next we need to do f lots of x minus x bar all squared. So we'll add an extra column, and we'll multiply the f column frequency by x minus x bar all squared. So 6 multiplied by 1.44, 13 multiplied by 0.04, 10 multiplied by 0.64, and 1 lot, or 3.24. Then if we add up this column here, we get 18.8, which must be the sum of f x minus x bar all squared, which is the numerator for our formula. So all we need now is the denominator for the formula, the sum of f, which is just the sum of the frequency column. The sum of f was 30. Then we can just substitute these values into the formula. So the numerator, the sum of f x minus x bar all squared was 18.8, and the sum of f on the denominator is 30. We just type this into the calculator to find the standard deviation. So for this one it's 0.7916. The units would be the same as the units of x, so in this case it was number of games consoles. Let's also look at how we can use the alternative formula to work out the standard deviation. So for this one we're going to start with the fx column like we did before, and we'll multiply 0 times 6, 1 times 13, and so on, but we did these values a moment ago. Then we'll work out the fx squared column. So to do this, we multiply the f column by the square of the x column. So we take the x values and we square each of them and then multiply them together. That will give you these values here. Now if we add up the f column, we get the sum of f, which was 30. If we add up the fx column, we get the sum of fx, which is 36. And if we add up the fx squared column, we get the sum of fx squared, which is 62. Then it's just a case of substituting these values into the formula. So the sum of f is 30, the sum of fx is 36, and the sum of fx squared is 62. Then we would type this straight into the calculator and you'll get the same value we did before, 0.7916 games consoles. Now just like before, this is also possible with a calculator. So I'll show you how we do that now. We go into the statistics mode like before, select one variable, and then we just type in the x values. So we've got 0 games consoles, 1, 2, and 3. And then we also type in the frequencies. So 6, 13, and we have 10, and 1. And then just like before, for a list of data, we press the execute button twice, and it will calculate the standard deviation. You can see this matches our value, 0.7916. You also need to be able to do this if the data is in a group frequency table, like this one here. The way we do this is replace the x values, or in this case the t values, with the midpoint of the interval. So we add a midpoint column, and the midpoint of 0 to 30 is 15, the midpoint of 30 to 60 is 45, and then we have 75 and 105. So when we do this on the calculator, we go into statistics once again, but when we type in the x values, we're going to use the midpoint values instead. So 15, then 45, then 75, 105, and then of course we need to put in the frequencies, so we need to put in 4, 11, 6, and 5. Then we just press execute once and a second time, and we get the standard deviation. So for this one, the standard deviation is here, 29.0988928, and the units would be minutes. It's important to understand that this is only an estimate for the standard deviation. This is because we don't know the actual time values. Instead, we use the midpoint for the purposes of the calculation. So far, when working out the variance or standard deviation, we've had to work out lots of different values, like these ones here. Sometimes the exam question gives you these values instead, and you just need to use them in the formula. Let's have a look at how some of these questions could be worded. In this question, it says, a YouTuber recorded the number of views of their 10 most recent videos, and we're told that the sum of x is 80,200 and the sum of x squared is 680 million. The question wants us to work out the standard deviation to the nearest view. So for the standard deviation, we've got two formulas that we could use, and for this one it makes more sense to use the second formula because we've been given the value of the sum of x squared. So all we need to do is substitute these values into the formula. We know the sum of x squared, that's 680 million. We actually know n as well, that's how many videos there are, and we're told it's 10. So n is 10. We can also work out the mean by doing the sum of x over n. The sum of x is given in the question, that's 80,200, and n is once again 10 for the 10 videos. If we work out the mean, we end up with 8,020. So all we need to do now is just substitute these values straight into the formula. We could type this into the calculator and we'd find the standard deviation to the nearest view is 1,918 views. Let's try another example. So in this one, it says the masses of a litter of kittens are recorded. And we've got the sum of m, which is 585, and the sum of m minus m bar all squared is 65.5. This time we're going to work out both the mean and the standard deviation to one decimal place. So for the mean, m bar, we need to do the sum of m over n. The sum of m is given in the question, that's 585, and n would be the number of kittens, which is 6, given in the question as well. So we do 585 over 6, which is 97.5 grams. So that's the mean done. Now for the standard deviation. We've got two formulas to choose from, and given we've been told the sum of m minus m bar all squared, we're going to use the first formula, because that has the sum of x minus x bar all squared. Obviously, we're going to replace the x with m, so the sum of m minus m bar all squared. So we've been given that value in the question is 65.5. And we know the value of n, that's still 6 kittens, so we just type this into the calculator, and this will give you a standard deviation of 3.3 grams. Now there's actually one more way of writing the standard deviation formula. If we take the original formula here, there's a summary statistic which we call SXX, which is equal to the numerator of that fraction, so the sum of x minus x bar all squared. So instead of writing sum of x minus x bar all squared as the numerator, we could just write SXX as the numerator instead. You need to be aware of this, and this value could be given in questions. Let's have a look at an example. So in this question we're told, the lengths of 20 javelin throws are recorded, the sum of x is 1487, but SXX is 1730.55. And we need to work out the standard deviation of x to one decimal place. So remember, SXX is just the same as the numerator of the original formula, the sum of x minus x bar all squared. So all we need to do is replace the numerator, SXX, with 1730.55, and n will be the number of javelin throws given in the question, which is 20. We then type this into the calculator and you'll get a standard deviation to one decimal place of 9.3 meters. So you just need to be aware that SXX is another way of writing the sum of x minus x bar all squared. Now let's try one more question where values are given to us to use in the formula, but this time with a table. So the ages of 1,300 pupils on the first day of school are shown below, and here's the table. We've been told the sum of fx and the sum of fx squared, and we need to work out the mean and standard deviation. So for a question like this, you have a choice. If you wanted to, you could just type the whole table into the calculator and it will work out the mean and standard deviation for you. Or you could use the information given in this question. Remember, the formula for the mean is the sum of fx over the sum of f when we're working in a frequency table. The sum of fx is given to us, 17,685, and we also have the sum of f, that's actually given in the question, it's 1,300 pupils. So we can type this into the calculator and we'll find the mean of 13.6 years. Then for the standard deviation, we need to use this formula here because we're working in a frequency table. We've been given the sum of fx squared, and the sum of f, 1,300 again, and we already know the sum of fx over the sum of f because that's the mean, which is 13.6 years. So you could type this into the calculator and you'll find the standard deviation to be 1.88 years. Because the variance and standard deviation are measures of spread, we can use them to make comparisons of datasets. Imagine we had this data here, which was the attendances of some Year 12 students, and this one, which is the attendances of Year 13 students. Well, all of these are given as percentages. A question could ask us to compare the mean and standard deviations of the attendances. So I'm not going to work these out manually, I'll just tell you the answers now because you probably know how to calculate these. The mean for Year 12 x bar is 87.7, and the mean for y bar is 86.4. So x bar is higher than y bar, which means we could say that Year 12 students had a higher average attendance. Now if we do the standard deviations, sigma x, which is the standard deviation for Year 12, is 5.1, and sigma y, the standard deviation for Year 13, is 26.7. Remember, the standard deviation is a measure of spread, so a lower value means the data is less varied or less spread out. So since the Year 12 have a lower standard deviation, we could conclude that the attendance for Year 12 students was less varied. Now, looking at this data in detail, you might not necessarily agree with some of these conclusions. You might have spotted this particular value here, an attendance of just 3%. Let's now have a look at what happens if we use the median and the interquartile range to make these comparisons instead. If we were to work out the median, we'd look at these two values here in the middle of the data. So for Year 12, the median Q2 is 85%, and the median for Year 13 is 94%. If we worked out the interquartile ranges, that's the difference between the upper and lower quartile. For Year 12, the difference between these two, and Year 13, the difference between these two. So for the interquartile range, we get 11% for Year 12, and 9% for Year 13. In both of these, we end up with the opposite conclusions. So if you look at the median for Year 12, it's actually lower at 85% compared to the median for Year 13 of 94%. This is because the median isn't affected by the extremely low value of 3%. A similar story happens with the interquartile range. Previously, we said that Year 12 had less varied data. Actually, using the interquartile range, Year 13 has less varied data. This is because the interquartile range is not affected by that extreme value of 3%. So it's important to understand that the standard deviation, like the mean, is affected by these extreme values. And so is the variance, since the variance is just the square of the standard deviation. So if you do have extreme values, it might be worth considering using the median or interquartile range over the mean or the standard deviation. That's not to say you always should, it depends on the reason for that extreme value. Sometimes it might be worth including it. You also need to have an appreciation for what happens to the mean and standard deviation if we either add or remove a value from a set of data. Let's take this set of data here. If we were to draw it out, it would look like this, and the mean of this set of data, x bar, is 24. Let's add in a number to this data that's below the mean. For example, if we added in the value 21. When we include this value into the dataset, the mean actually decreases. It goes down to 23.5. This is because 21, the value we added, is below the mean. If we added in a value that's even further below the mean, for example, the number 3, then the mean will also decrease, but by even more. So this time the mean will decrease all the way down to 20.5. Conversely, if you add a value that's greater than the mean, for example, if we added 36 to this dataset, then the mean will increase. This time it will increase up to 26. And what happens if you add a value that's equal to the mean? So if we added in the value 24? Well, in this case, the mean will remain unchanged. In fact, you could add as many 24s as you wanted into this dataset, and the mean will remain 24. Let's also look what happens if you remove a value from a dataset. So let's remove the lowest value here, the number 1. If you remove a value that's below the mean, the overall impact of this is that the mean will increase. So in this one, it would increase to 29.75. If instead you remove the value greater than the mean, so if we remove the 39, then the mean will decrease, this time down to 20.25. And if you had removed a value that was equal to the mean, it will remain unchanged. Let's summarize what we've just covered. If we add a value that's greater than the mean increases. If we add a value that's less than the mean decreases. If we add a value that's equal to the mean, then the mean will be unchanged. And of course, removing values. If we remove a value that's greater than the mean will decrease. If we remove a value that's less than the mean will increase. And if we remove a value that's equal to the mean will remain unchanged. We also need to look at this idea with the standard deviation. Unfortunately, this is not quite so straightforward. The standard deviation for this set of data is 14. I'm going to mark on a value that's one standard deviation below the mean. So I'm going to subtract the standard deviation 14 from the mean 24. That will give me 10. So this value here is one standard deviation below the mean, or x bar subtract one standard deviation. I'm also going to mark on the value that's one standard deviation above the mean. So I'm going to add 14 onto the mean of 24. This will be 38. So this is one standard deviation above the mean. We're going to look at what happens if we include an extra value that's within one standard deviation of the mean, so somewhere in this region here. So if we added in an extra value of say 21, what will happen to the standard deviation? Well, this will actually decrease down to 12.829. If instead we added a value all the way up here close to the boundary, say 37, the standard deviation will have still decreased, so for this one it's 13.668, just not by as much. And if we added in a value that was equal to the mean, the standard deviation will still decrease, this time to 12.780. This is because when we add in extra values that are relatively close to the mean, the data becomes less spread out. If we add values that are relatively far from the mean, the data will become more spread out. So it doesn't matter whether this value is greater than or less than the mean, it matters how close to the mean it is. So if it's within one standard deviation of the mean, the standard deviation will decrease. Next we'll have a look at the values that are in the opposite regions. So more than one standard deviation from the mean. So either below 10 or greater than 38. Now you would hope and expect that any of these values would lead to an increase in the standard deviation, but it doesn't quite work like that. If the value we add in is exactly one standard deviation below the mean, so it has value 10, then the mean itself will actually decrease because of what we looked at previously. For this one, the mean will decrease down to 21.7. This means because we've added in this extra value, the mean has actually shifted. So the standard deviation still decreases here. It decreases down to 13.8. If we then go into the region even further, for example if the value was 9 rather than 10, the mean will decrease even further, but only by a small amount, down to 21.5, and the standard deviation will now be slightly higher, 13.95, but it's still decreased from its original value of 14. We actually have to go all the way across here to the value of 8. This will decrease the mean ever so slightly further, down to 21.3, and the standard deviation will now have actually increased to 14.1. The same idea applies at the upper end. So if the value we added was exactly one standard deviation above the mean, so 38, then the mean will slightly increase, all the way up to 26.3, and the standard deviation will still decrease, down to 13.8. But to get the standard deviation to increase, we need to go a little bit further, up to 40. The mean will increase ever so slightly, up to 26.7, and now the standard deviation will be 14.1. Let's summarize what we've looked at here. So if we add a value that's within one standard deviation of the mean, then the standard deviation will definitely decrease. And if we add a value that's significantly more than one standard deviation from the mean, the standard deviation will increase. I've used the word significantly here because, as we showed a moment ago, if you're only a little bit more than one standard deviation away from the mean, the standard deviation will still actually decrease. Fortunately, in exam questions it's usually obvious. The value that you add in might be 2 or even 3 standard deviations away from the mean, in which case it's very obviously going to increase the standard deviation. The opposite statements are also true if we remove a value from the dataset. So, if we remove a value that's within one standard deviation of the mean, this time the standard deviation will increase. If we remove a value that's significantly more than one standard deviation from the mean, this time the standard deviation will decrease. Thank you for watching this video, I hope you found it useful. Check out the one I think you should watch next, subscribe so you don't miss out on future videos, and why not try the exam questions I've put in this video's description.